Good morning. Today we are continuing our investigation into some probability. So today's lesson is about comparing experimental and theoretical probability. Those are the two that we looked at last week. And then you'll have some practice. And there's actually only one more lesson for today. So we will be all done with probability as of tomorrow. So there is a lesson note if you would like to print it out and follow along. Okay, so first I'm just going to remind you what the definitions were of both theoretical probability and experimental probability. Okay, theoretical is the mathematical probability that is calculated without actually doing the experiment. Okay. Stick that in there. All right. The equation for your theoretical probability, I'll just write it out on the side here. It was the probability of the event is equal to the number of successful outcomes over the total number of possibilities. Okay, so total possibilities. Awesome. Next, the experimental probability is the probability observed when my keyboard is freaking out a little bit. Probability observed when performing an experiment. Okay, so for this one, your equation, the probability of an event is the number of successful trials, so how many times you actually got a success, divided by the total number of trials. Okay, so experimental is when you actually do the experiment, and theoretical is what should happen. Okay, so without actually performing the experiment. So the theoretical probability of rolling a 2 with a single die is 1 over 6. Right? 6 outcomes on a die, one of them is a 2. However, if you try it, do you suppose you will roll exactly 1 2 in every 6 trials? So no, reality and theory are not necessarily the same, right? Like, you could, right? But probably not, because when you're doing things in reality, it's not actually what it should be all the time. Okay? Let's suppose that we're tossing 10 coins at once. Okay? How many heads should occur in each toss? So if we have the probability of heads when you're rolling a die, when you're flipping a coin, is 1 over 2, right? There's 1 head and there's 2 total possibilities. So the number of expected heads is going to be the probability of heads times the number of trials. All right, so in our case, it's going to be 1/2 times, for flipping 10 coins, that's 10. So the expected number of heads is 5. All right, but why might we not necessarily see 5 heads every time? So probabilities are like averages, okay? So if the experiment is done enough times, the experimental probability gets closer to the theoretical probability. Okay, so the more times you do it, the closer it'll get to what it actually should be, or the average that you are expecting. Okay, so we might not necessarily see 5 heads every time, but the more times we do the trial, it should get closer and closer to 5. Okay, it's like an average. So let's do an example here. This is actually one of the questions from your practice for today, so you're welcome. Okay, so a modified dartboard has equally spaced sectors containing the numbers 1 through 20. What is the theoretical probability of hitting the numbers 18, 19, or 20? So we're going to do the probability of 18, 19, or 20 is equal to, so it's a theoretical probability. So it is how many total possible outcomes are there? Sorry, successful outcomes are 3 over the total possible outcomes of 1 through 20. There are 20 options there. Okay, so there are 3 successful possibilities over 20 total possibilities. All right, so that is your theoretical probability. But part B says in 75 of the first 80 throws, a dart player hits that number. So this is going to be the experimental probability of getting 18, 19, or 20. Okay, they got 75 successes out of 80 throws. Okay, and we always reduce our fractions. This is 15 out of 16. Okay, which is a lot higher than the theoretical probability. But that's because in darts, you're aiming for something specific, right? It's not totally random which number you hit. Okay, so we're going to say no. Sorry, the question says, would you expect the experimental probability to approach the theoretical probability? No, because each outcome here is not equally likely, since the player is actually aiming at 18, 19, or 20. On the board, rather than making random shots, right? So it's not the same as flipping a coin or rolling a die. You're actually aiming for something on a dartboard usually. And if you're any good at darts, your chances of hitting those numbers is higher the more that you throw the dart. Okay? So a couple more examples here on the next page. Suppose a couple would like to have 3 children. Okay? So we're going to determine the theoretical probability of having 2 girls and 1 boy. So we're going to make a tree diagram. So for child 1, child 2, and child 3, let's see here. So when you have a child, it's pretty much 50-50 whether you get a boy or a girl, right? So our first branch of our tree diagram is a boy or a girl. After that, your second child, if you have a boy, again, you could have a boy or a girl. If you had a girl, your second child could also be a boy or a girl. And then from there, for the third child, again, if you had a boy, you could have a boy or a girl. If you had a girl. Okay. There we go. Okay, so there's a tree diagram showing the possible outcomes, the theoretical outcomes for having 3 children. I'm just going to pause for a second and write down the possible outcomes. There we go. So here are your possible outcomes. There's 8 of them. It's really similar to when we did the flipping the die tree diagram. Not flipping a die, flipping a coin tree diagram from last week. Okay, so now the question asked, what is the probability of having 2 girls and 1 boy? Alright, so we're going to count the number of possibilities where there's 2 girls, 1 boy. So we've got girl, girl, boy there, girl, girl, boy, and girl, boy there. Okay, so the number of successes is 3 over the total number of possibilities is 8. Okay, so we could also write that as a percentage. It's 38%. Okay. Part B says, explain how your answer in Part A can help determine the theoretical probability of having 2 boys and 1 girl. So if you look up here, the possibilities of having 2 boys and 1 girl are 1, 2, and 3 again. So we can say the theoretical probability of having 2 boys and 1 girl is the same as having 2 girls and 1 boy. Right there, there are 3 possible ways that can happen. So they're both 3 out of 8 or 38%. Determine the probability of having at least 1 girl. Okay, so we'll go the probability of at least 1 girl. So we'll go up and count. There's a girl there, 2, 3, 4, 5, 6, 7. There's only one way you can have no girls, right? So the probability of having at least 1 girl, there are 7 successful ways that can happen over 8. So there's an 88% chance, if you're having 3 children, that at least one of them will be a girl. Determine the probability, the theoretical probability of having 3 girls. Okay, so probability of 3 girls. There's only one way that can happen out of your total of 8, so that is 13% chance of having all 3 girls. Suppose a couple hopes to have a boy first and a girl second. So what's the probability of that happening? The probability of a boy, then a girl. So if we look back up at the top here, where does it happen? Boy, then girl, boy, then girl, right? And then no other ways that happen. So there are 2 ways that can happen out of your 8 possibilities. So that simplifies to a quarter, or 25% chance that you will have a boy first and a girl second. Okay, so here are your questions for today. I will post the solutions later on. Good luck.